Welcome to Mastering Solutions. This is another thin film problem, and so let's draw a picture first to see what's happening with our thin film. We're told that we have a laboratory dish, of course, and it's half filled with water. So on the bottom here of our thin film is the water, and that has an N of 1.33, of course. On top, obviously, is the air, which is an N of 1. And in the middle here, that's where this oil is getting dropped in. And so we have oil, and they tell us that the index of refraction is what we're looking for. So we have to figure that out. When we have light coming in, we're going to have some light that gets reflected off. Some gets refracted in or transmitted. And then we're going from a lower index of refraction to we don't know. Even though we don't know what the N is, we're not going to have an index of refraction less than 1. And so we're definitely going to have some sort of a phase change here. The question is going to be, are we going to have a second phase change right here? Some light will get transmitted, some will be reflected. And so this is what it'll look like. We just need to figure out if there's a phase change there. So really only two situations can happen. Either the N of the oil is greater than the N of the water, or the N of the oil is less than the N of the water. If it's greater than the water, then we won't have a phase change, so we'll only have one. If the N is less than the water, then we're going from a low now to a higher index of refraction, so then we would have two phase changes, one here. So to figure out which one we have to go with, we have to do a little bit of reasoning here. The question says that when we added 1 drop of this oil, so 0.5 microliters, they say that the intensity of the light from the surface is very low. So that's going to be destructive interference. And so with just this teeny amount of oil, the path length difference is very small, but we still got destructive interference. So that must mean that there was exactly just one phase change. And so we're going to be going with this. And so for one phase change for destructive interference, the equation that we'll use is going to be 2t is equal to m times lambda over n. Now we're trying to solve for n, right? And so we need to rearrange the equation for that. If we multiply both sides of the equation by n, the n's will cancel. So now we have 2 equals m times lambda. And now we can divide both sides by 2t. So n is, I'll write it up here. N is equal to m times lambda over 2t. How we know that we're using m equals 1 is because in the question they say that the light, as more drops are added, the reflected intensity increases and then decreases to another minimum. So we're going to be going with m is 1. We have the m, we have lambda, which we said is 600 nanometers for that, just the 1 drop of oil. We don't know what t is though, the thickness of the oil. So we have to, of course, figure that out. So we have a circular laboratory dish, and we're told that it is 20 centimeters in diameter and it's half filled with water. What is the formula for the area of a circle? Well, the area of a circle is equal to pi times the radius squared. We're not given the radius, we're given the diameter. So we have 20 centimeters in diameter. So the area in this case would be pi times 10 times 10 to the negative 2 for centimeters squared. So this is going to be the area of this little laboratory dish. But that's the area, that's not the volume. And they tell us that with 1 drop, because the point where we're looking at here is with just 1 drop added, and that's going to be 0.5 microliters. So the volume equation is going to be the area times the thickness. So if we rearrange this for the thickness, we'll divide both sides by the area. So the thickness is equal to the volume over the area. So we know what the volume is. We added 0.5 microliters. And to be clear, I think I might have misspoke. So what we're going to be doing is the reason that we're using M as 1 is because this 600 nanometer light where it's reflected is very low. That is the first minimum, which is going to be M equals 0. And so here they say they add 13 drops and we have a second minimum. So since we're doing destructive interference, the M values are 0, 1, 2, 3, whatever. And so we're using the second minimum, which is 13 total drops added. Let's go one more with this. So thickness is equal to the volume divided by the area, which we said is pi times the radius squared. So now we can plug this into our equation right here. So we have our final equation for n is going to be m, which we said is 1 times the lambda, which is going to be 600 nanometers, divided by 2 times the thickness, which we said is the volume, divided by pi times the radius squared. So this is our final equation. N is equal to 1. Then as we said, 600 times 10 to the negative 9 meters. That's divided by 2. Now the volume we said with 13 drops were added. So we have 13 drops and every drop had 0.5 times 10 to the negative 6 meters, and then that's divided by pi times the radius, which we said was 10 times 10 to the negative 2 meters squared. Okay, so we have 1 times 600 times 10 to the negative 9, and then we're dividing all of that by 2 times 13. Let's do like this. 13 times 0.5 times 10 to the negative 6. And that's divided by pi times the radius, or 10 times 10 to the negative 2 squared. Okay, so now we'll be multiplying that by the volume per one drop. And let me give us some more space. There's a really important point that we need to talk about here, and this is really a tricky point. I missed it at first too. What does the question tell us? They tell us that we have 0.5 microliters, but liters is not the standard SI unit, so we have to convert that to cubic meters. 1 liter is equal to 1 times 10 to the negative 3 meters, or 0.001 cubic meters. And what does micro mean? Well, micro means 1 times 10 to the negative 6. So when we write that out, what we have is 0.5, and then we have 1 times 10 to the negative 6, and then we have 1 times 10 to the negative 3. So this, when we convert this into cubic meters for standard SI units, we have 0.5 times 10 to the negative 9 meters cubed. So I know that might seem really confusing. We've gone over it in previous chapters. And so then when we plug this in here, we have 0.5 times 10 to the negative 9 cubic meters. And then that is divided by pi times the radius, which we said was 0.1 meters squared. And that's the squared is outside of the parentheses, of course. Okay, so now we have our full equation. So let's plug this into our calculator and see our final answer. So we have 600 times 10 to the negative 9, and that's divided by 2, 13 times 0.5 times 10 to the negative 9 for the volume times 13 drops. And then that is divided by the area, which we said was pi, times the radius, which is 0.1 squared. So now we have our answer. The index of refraction is 1.4. You could round that to 1.45. So the n is 1.45. And so our reasoning up here at the top of the question that the n is greater than that of the water was correct. We only had one phase change, and the n is 1.45 greater than water 1.33.